Okay, let's work problem 716, part A, because if you can do part A, I think you can do part B as well. It reads, ozone formation. O3 is ozone, okay? This ozone molecule is in the atmosphere, and the formation of it is actually a dynamic process. It's constantly being formed and reacted or removed in the upper atmosphere, up in the stratosphere. But this process begins, and it really requires sunlight with a wavelength less than or equal to 242 nanometers, which is a key cutoff wavelength, to be absorbed by oxygen molecules. Basically what happens is a photochemical reaction. A photochemical reaction is one that is mediated or driven by sunlight or photons. And the reason how these reactions generally work is that light with sufficient energy, here it needs to be less than 242 nanometers, acts to create either an excited state in a molecule or cleaves a bond. And that's the case of what's going on here in oxygen to create atomic oxygen, which creates a sequence of reactions that yield ozone or result in ozone formation. But the key step is that if we don't have light of this energy, we can't get the oxygen molecule to break apart. We don't get ozone. And this is actually why ozone is not formed by this mechanism in the low atmosphere, but it does form up in the stratosphere. There's a different reaction that can make ozone near the Earth's surface, which is called tropospheric ozone. That's what when we breathe that, it's a health risk. Okay, but that's from a different reaction. The one they're talking about here is one that occurs up high in the atmosphere, up in the stratosphere. Okay. Requires this light. Now we are to find the frequency and the energy of these photons that are required to make this happen. Okay, frequency and the energy. Now, hopefully at this point we're getting good enough at these problems to kind of see where we're going to go with it. Okay, we are given this number, which is a wavelength, 242 nanometers, nano being 10 to the minus 9, okay? You probably, or hopefully, have worked enough of these problems now to realize that we can convert between wavelength and frequency through using the velocity of our electromagnetic radiation, or the speed of light, c, which of course is 2.99 times 10 to the 8 meters per second. I set that equal to my wavelength times my frequency. Here, my wavelength is 242 nanometers. Now, notice the units here are meters. I need to convert to meters. I can easily do that, though, by multiplying by 10 to the minus 9, because that's my prefix for nano. I multiply that times my frequency, and I've got an equation that I can solve. So if I do so, my frequency is 1.24 times 10 to the 15th hertz or cycles per second, whichever one you prefer. Your analogous unit, cycles per second, so frequency unit. All right, so that tells me the frequency. Now that I'm armed with my frequency, I can go calculate the energy of a single photon of this light. I use this Planck's equation to help me do that. E is the energy in joules of a singular photon. H is Planck's constant. It's equal to 6.62 times 10 to the minus 34 joule second. And the frequency that I need to plug in is simply the number that I computed on the left-hand side, the 1.24 times 10 to the 15th cycles per second. You can see that the second units cancel out, and we will be left with joule units once we're done. And if I do the math on that, I get 8.18 times 10 to the minus 19th. Joules. That's the energy that's required to start this process of ozone formation. Okay? in one singular molecule of oxygen. So that's the energy of the photons. Now, there are other problems like this, and I don't think I've seen one in your textbook quite yet. Sometimes you're asked to calculate the energy of 1 mole of these photons. So I could say, okay, lights of 242 nanometers, calculate the energy of 1 mole of these photons. Remember, photons are kind of our fundamental particles of light, if you can think of it that way. Much like atoms are our fundamental particles of material, okay? So if I asked you to calculate the energy of 1 mole of this type, or photon at 242 nanometer wavelength, all you really need to do is take the energy of 1, which is 8.18 times 10 to the minus 19. So when we use this equation over there to compute the energy, that's for 1 photon of that type of frequency. Okay? If I need to do a mole of photons, so if 1 is that, why don't I just multiply by Avogadro's number, 6.023 times 10 to the 23rd. I multiply by that, and that gives me my energy of a mole. Okay? So it's no big difficult problem if you're ever faced with having to calculate the energy of a mole of photons. You just have to know what you're calculating. You have to know that this is the energy of a singular photon. If you need a mole of photons, this is how many that's in a mole, because a mole is just a counting unit. 6.023 times 10 to the 23rd of anything is a mole of them, right? So pretty simple stuff. So hopefully you can get this.